This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
We've got lots and lots to cover. So my goal today is to explain to you, I guess, two main things. One is a little about the large-scale electricity industry in Australia, particularly around coal and gas-fired generation. And coal and gas still produces between 60 and 70% of the electricity in this country. And secondly, to tell you about the technology of coal-fired power stations and gas-fired power stations. Okay, so that's my goal. Two things. Lots and lots of pictures. We're going to do a tiny bit of thermodynamics, not in mathematics, but qualitatively, just with some pictures on the whiteboard. And we've got a couple of short videos as well, just to give you a feel for the sorts of things we're talking about. Please stop me and ask questions as we go through. Happy to ask any questions, or we can have a discussion at the end. Okay, so as I said, we're going to look at some power industry background. We'll look at coal power plant technology, gas turbine power plant technology, generators, electrical and control systems. We'll look at something called grid frequency control, and then have a quick review at the end. Okay, so first things, power industry background. What is a megawatt? So I'm sure many of you have done engineering of some sort, and in the power industry we talk about megawatts. So a megawatt is an instantaneous measurement of power. To put it in context, a small car engine has a power of around 100 kilowatts, right? 0.1 of a megawatt. Typical house consumption is 1 to 2 kilowatts. Okay. Typical large power plant capacity is something in the range of 200 to 1,000 megawatts. Okay. A large power station like Kogan Creek, the largest unit is a 750 megawatt unit at Kogan Creek in Queensland. And the largest power station in Australia has 4 720 megawatt units. Okay. The installed capacity of the grid on the east coast of Australia is about 48,000 megawatts. So we're going to come back to some of these numbers later on, okay, just to give you a feel for the scale of what we're talking about. So in addition to megawatts in electricity, we talk about megawatt hours. So megawatts are instantaneous power. Megawatt hours are amounts of energy. Okay. So what's a megawatt hour? So it's a measurement of energy delivered or consumed. A typical house consumption is something in the order of 10 to 20 kilowatt hours a day. The annual energy delivery in the NEM, the National Electricity Market, that's the East Coast market, is around 190,000 gigawatt hours. So on average, if you divide 190,000 by 365 and 24, you get about 22 gigawatts. That's 22,000 megawatts of average capacity. Okay? So 22,000 megawatts, you think about a unit size, we'll talk about units all the way through this discussion, of something in the range of 200 to 600 or 700 megawatts. So that's quite a lot of units that are generating at any time in order to keep the lights on the east coast of Australia. So what this means, with an average load of 22 gigawatts, many coal plants are running below full load all the time. Many gas turbine plants are peakers that run something like less than 1,000 hours a year. Also, we note that most renewable generation has inherently low capacity factors. So wind and solar, which is not really the focus for today, they have 30% capacity factors. So they come and go and come and go, and everybody else has to respond. And we also note that the grid needs something called spinning reserve. We'll come back to this when we talk about frequency control. Okay? But what happens is, on a grid, at any point, and this is a very important point on the power industry, it's the one industry that has very little storage. So at any point in time, the power industry has to produce exactly the amount of power that the consumers want to use. We'll come back to that point a little later. Okay, this map shows the major coal-fired power stations in Australia. So you'll see here in Queensland, there's quite a large group of power stations all burning black coal. Okay, Kogan Creek, 1 by 750 megawatts. Gladstone, 6 units of 280 megawatts. Stanwell, 4 units of 350 megawatts, and so on. New South Wales, large number of units that are 660 and above, all burning black coal. In Victoria, number of units burning brown coal. And then over here in WA, number of units burning something in between, sort of a wet black coal. Okay, so they are all of the large coal-fired power station units in Australia. Then gas turbine units, and we'll talk about what coal units and what gas turbine units look like in a minute. So there's a larger number of gas turbine units. They are typically smaller, and you can see in this picture, the names in black are open cycle units. So those are pure gas turbines. The ones in red are combined cycle units. They combine a gas turbine and steam turbine cycle, and we will look at what that means in a few moments. Okay, so these are all the major grid-connected power plants. There are some that are not grid-connected and lots that are smaller, but these are the major ones. Again, to give you a feel of how many are we talking about. Okay, now it's quite important to understand this NEM on the East Coast. So the national electricity market is this high voltage grid. So these coloured lines are the different voltage transmission lines down the east coast of Australia. That transmission system is the longest, skinniest transmission grid in the world. Okay? And it actually consists of a number of nodes that have weak interconnections. So the nodes are all around the capital city, so around Brisbane, Sydney, Melbourne, Adelaide and Hobart. And then the transmission systems are really designed per state to transmit power generated at power stations within that state to the major capital city, and there are relatively weak interconnections between the states. That makes Australia really, really unique. And with the development of renewables, typically wind and solar that are out in remote areas causes all sorts of interesting challenges to the transmission system because those renewables are generating power where no power used to be generated. Okay? Today's not really about renewables, we'll touch on them shortly, but actually this grid has challenges even for the coal and gas generators in that as the weather changes and demand changes in each state, there are constrained abilities of the transmission system to transmit power from state to state. And the same happens here in WA, where you've got a grid around Perth and another small grid here around Karratha, and then there's a small grid around Darwin. Okay? All right. So, some interesting things about electricity generation growth. So, historically in Australia, there was a linear growth in electricity demand that really followed population demand. And around 2008, 2009, that connection between population growth and electricity demand stopped. As we hit the GFC, as people got more efficient with using electricity, and as electricity prices went up. Okay? And renewable generation started to grow. What we see in this graph is the change in time of the mix of power generated in Australia. So you can see here we've got black coal, brown coal, natural gas, and then renewables. And this graph shows the mix of renewables. So you can see hydro, while it wobbles around from year to year, has been relatively steady in complete volume. And then we've got a growth in wind over the last decade or so. Biomass goes up and down, and then a significant growth in solar over the last decade. Okay. But still the majority of power is produced by fossil fuels. And this graph shows the difference between the states, which is really, really significant. So New South Wales is a black coal state, Victoria is a brown coal state, Queensland is black coal, WA is some coal but heavily gas, South Australia heavily gas and wind, Tasmania nearly all hydro, Northern Territory nearly all gas, and then you can see the mix as Australia. So the different states have very different energy mixes. Okay, so that's a really quick run through what are megawatts, what are megawatt hours, what does the country look like in terms of where the energy comes from. Now we're going to take a section to look at what do coal-fired power stations look like. So this photograph is of a coal-fired power station in Germany. You can see it has cooling towers, fully enclosed boiler. We're going to look at all of those components in a second. Okay, so first thing, coal-fired power plants are located and designed relative to a number of factors. First thing is fuel. So because the fuel is coal, coal is a rock, and coal from area to area and even within a nominal area changes quite dramatically in its combustion characteristics. So you have to know what fuel you're going to burn when you design your power station. the boiler, the ash handling, the flue gas handling, all changes depending on the characteristics of fuel. We then need a transmission connection, and transmission lines, roughly speaking, cost about $1 million a kilometre. So if you have a 300-kilometre transmission line to your power station, it's going to cost you $300 million. That's quite a lot of money. You need to take account of what that costs. We need cooling water. We'll see why shortly. So that can either be seawater, river water, or lake water. We need somewhere to dispose of waste, so that's the ash that's produced when you burn the coal. So quite a lot of the coal, something between 10 to 20 or 30% of the coal is non-combustible, let's call it sand and rock, and that comes out as ash. You have to do something with that. We have to have suitable geology. So around a coal-fired power station, we will have several dams, and we've got massive structures that need good geological strata to support them. And finally, we need all sorts of things like environmental approvals and conditions. So that means building a coal-fired power station is quite a complex thing. What we find is most Australian coal-fired power stations are located next to a coal mine. Okay? In the 30s, 40s, 50s, we had coal-fired power stations located in the centre of big cities. So Melbourne, Sydney, Brisbane, Perth all had coal-fired power stations within the city limits, normally on the river that city is built on. Okay? That's changed over the years. Those power stations were also quite small by modern standards. Nowadays, nearly all Australian coal-fired power stations are based next to a coal mine. Okay, so what do these things look like? So you can see this is a Google Maps picture of Bayswater Power Station in New South Wales. It has 4 units, each 660 megawatts. It is a massive industrial undertaking. This power station was actually used as a set for one of the Matrix movies. Okay? It's so big to look at. You could just about fly a helicopter down the turbine hall. It's that large. So you can see here from a very high distance, the power station has, so this is the power station proper, 4 big cooling towers. This area here is the coal storage plant. I believe this is the largest coal storage plant in Australia. A freshwater make-up dam, a cooling water make-up dam. This is the ash dam. So the ash, after combustion, is mixed with water and pumped into this dam where it settles out, and eventually this dam will be filled in 20 years. Okay? Here's the switchyard that connects the power station to the transmission grid. So if we go closer in, see here again, switchyard, cooling towers. This is the turbine hall with 4 turbines in it. There are 4 boilers, gas cleaning plant, and 2 big stacks. You can see part of the coal handling plant here. The car park is in this area. The little dots you see are the cars. So this is a really, really big place. And coal-fired power stations in general are some of the largest industrial undertakings in the country. Okay, this is then a diagrammatic of a typical 2-unit power station. So what do we have? Coal stack, the coal reserve here. This is the stack from the boilers. Gas cleaning plant, boilers where the coal is burnt and steam is produced. Turbine house, which has the turbine generators in it. Transformers which take the electricity at, say, 20,000 volts from the generators, step it up to, say, 500,000 volts for the transmission system, and then transmission lines to take the power away. Okay? And most power stations look like this, 2 units or 4 units or 6 units, with the units being independent of each other. Okay, so what do we do in a coal-fired power station? We take coal, which is carbon and other chemicals. We burn that coal, we give off heat, we use that heat to boil water and then superheat the water to produce superheated steam. We then expand that superheated steam through a turbine. The thermal energy is converted into rotational mechanical energy. That rotational mechanical energy in the turbine turns a generator which produces electricity which is transmitted to the grid. Okay? Now, what I would like to take you through is my small qualitative thermodynamics lecture. So those of you who've done thermo, please excuse this for a minute, but what I'd like to do is talk about a steam cycle in terms of a kettle. So if we've got a kettle that is half full of water and we start heating it, and I draw a picture like this. Okay? So I'm heating this water, it's heating up, and we get some stuff coming out of here that we can see. What's that stuff? I'm looking for some audience interaction. What's that stuff we can see? Someone? What is it? Very good, water vapor. So most people will say steam, that's incorrect. The stuff you can see here is water vapor. The invisible part in here, that's steam. Right? Steam is an invisible gas. This is starting to cool already and becoming water vapor. Okay, so if I'm heating the water in here and it starts bubbling and producing steam, it's at 100 degrees C, isn't it? And it's at atmospheric pressure roughly. Okay, if I put a valve on here and I throttle off that flow of steam out of the spout of the kettle, what's going to happen? Okay, so I start to get a stream of steam coming out of the valve. What happens in here? Well, eventually, yeah. So what happens in here is the pressure goes up, okay? As the pressure increases, the boiling point of this water increases. So it goes from 100 to 110 to 120 and so on as the pressure increases. And then I'm starting to get superheated steam out here. I'm getting steam that's much hotter than 100 degrees C. Yeah? Now, if I keep heating this thing, the other thing that happens is eventually the water level starts to drop, doesn't it? Okay? All right, so let's say I connect a water supply onto this thing because I want to keep the level in the kettle constant. So if I want to get water to flow into this, I actually have to increase the pressure of the water to be slightly above the pressure in here, don't I? So I need some sort of a pump in here from my tank of water that I've got to pump water into that kettle because the pressure is above atmospheric, isn't it? Okay, so if I've got a continuous process now where I'm pumping water into my kettle, I continue to heat it, and I'm producing steam that's superheated out of this thing. It's superheated because I'm throttling it, and the pressure here is above atmospheric. Does that very simple picture make sense to everybody? Again, looking for some audience interaction would be great. Okay, so yeah, so that's pretty straightforward, but I find that very helpful to have that simple discussion first before we start talking about this picture, which is a picture of a steam turbine power plant or a coal-fired power plant steam cycle. Okay, so let's have a look. What does this picture mean? This is not to scale. We're going to have a look at some pictures that are more to scale in a minute. This box here diagrammatically is a boiler. The irony is the boiler is actually physically the biggest part of this cycle. So in this boiler, I'm burning coal, and the walls of the boiler are made up of tubes around that sort of diameter, and they are full of either water or steam, depending where in the cycle we're talking about, and they're absorbing heat that's given off by the coal combustion. Okay? So I'm producing superheated steam that goes through some valves into my HP turbine where it's expanded, comes out lower pressure and somewhat cooler. It goes back into the boiler and is reheated, comes into an IP turbine where it expands typically in two ways, comes out of the IP turbine across to an LP turbine, expands again, and then drops out of the bottom of the LP turbine into a condenser. Condenser is a very large box, I guess you call it, which has thousands of tubes going through it with cooling water through them. The idea of the condenser is to cool that steam that's been ejected from the LP turbine into water, which is then collected through a pump, pumped around this cycle. It's pre-warmed again through a deaerator. So these things are feed water heaters, through a deaerator, which is heating the water as well. Another pump, a feed pump to get hot, really high pressure, through some high pressure heaters, back into the boiler where it's boiled, made steam, and around the cycle again. Okay? So there's a very quick run through a steam cycle. A couple of things to note. The efficiency of this picture depends on having the highest pressure and temperature at the inlet to the turbine and the lowest pressure and temperature at the outlet. Okay? On a modern utility scale unit, the pressure and temperature at the inlet, pressure might be above 20 megapascals, so it's 200 atmospheres, and temperature will be well above 540 degrees C, in some units approaching 700. Okay, so this is very, very high pressure, high temperature steam. And then as it's exhausted from the LP turbine, because you've got cooling water flowing through this condenser, the pressure at the exhaust of the turbine is subatmospheric. Okay, so inside the condenser, if you punch a hole in the side of the condenser, you won't get steam coming out, you'll get air rushing in, because the steam condensing causes a vacuum in that condenser. Does that make sense? Okay. Okay. The other thing I find interesting is to give you a feel for the energy level of this steam. If you have a pinhole leak in the wall of the boiler, okay, if that wall is there and there was a pinhole leak, and I've got steam at 20 megapascals and 600 degrees C, what happens is the first thing you would sense is an ear-piercing scream, because that steam is coming out at supersonic speeds. There would be a cloud of water vapor somewhere over here, and if you walk through the superheated steam jet that's coming out, you would be vaporized. Okay, so this is really high energy stuff that we're talking about. Okay, so what do these things look like? So this picture shows a cross-section of a typical, it's not quite to scale, of a typical coal unit. So what we have here is the main furnace with the coal burning. That coal comes from coal bunkers. It goes through a pulverizing mill where it's turned into something that would be like a black flour. So it's ground to a very fine consistency and then blown by this primary air fan, blows air through here and is transported up to burners as a suspension in air. It then comes out of the burners and burns in flames that are 6 to 7 meters long. So these burners, we'll have a look at pictures of these in a minute. These are very large flamethrowers, okay? And then the heat is given off in this furnace. The walls of the furnace are made up of tubes which have water in them. And then there are more tubes hanging in the gas path here which have steam in them. And the heat in the gas is given up to those tubes to give you superheated steam, right? The gas, combustion gas, then flows out through this air heater, up through, in this picture, a precipitator where you clean the dust and ash out of it, and then is ejected up the stack where hopefully it comes out looking fairly clean. Okay? In the meantime, the superheated steam comes out of the boiler into this HP turbine, into the IP turbine, LP, back into the condenser and round again. Okay? And that turbine is driving a generator here, which is connected electrically to a transformer, which connects you to the grid. So if you can go away with an understanding of that picture, you have a pretty good understanding of how a coal-fired power station works. Okay. All right. So if we look at now some slides more of a boiler. So again, here you can see this is more to scale of a boiler. You can't see the turbine in this picture. We've got the coal bunker rather, mill, 4 levels of burners either side of this particular furnace with ash dropping out of the bottom, superheater pendants, reheater and economizer in the back path, gas cleaning and the stack. Okay, and then photographs. So this is a 2-unit power station. Here we're looking at the back of the boilers. This is the gas cleaning equipment here. The turbine house is at the front here, you can see. So there would be 2 turbines at the front of this thing. These are 2 units. And similarly here, this is a cross-section of a single unit where you can see the boiler cross-section, turbine here up on its foundation with the condenser hanging below. And for scale, you can see this is a human being walking across the concrete here. So again, it's a very large piece of equipment. And then internally, all of these tubes are typically that sort of diameter, okay, with the pendants here hanging in the gas path, typically being superheater, reheater or economizer pendants, and then the walls are water walls. And there are hundreds of kilometres of these tubes in one boiler. Then a picture of a burner. So these were the burners we saw in a typical boiler. There'll be something like between 30 and 40 of these burners, typical boiler. This picture, does not show the coal flame. This shows the diesel oil igniter burning. And you can see there's no coal flame currently coming out of this thing. It's about to start burning coal. Once the coal flame starts, it's just so bright you can't see anything. But this is a diesel oil ignition flame. So when you start burning coal, firstly you have a diesel flamethrower, then you bring coal and you ignite the coal and then you shut the diesel off. Then flue gas cleaning. So as we've said, the gas that comes out of the boiler has dust in it, ash, and we need to clean that ash out, otherwise it's going to come out of the stack and go across the countryside. Two main technologies. One is fabric filters. These are like very long, thin vacuum cleaner bags. You can see these are being installed here in this picture, and there will be thousands of those bags in one unit, and they are regularly mechanically shaken to shake the dust off as the dust collects, and then that dust is sluiced away and taken to the ash dam. The other technology is electrostatic precipitators, where you don't have vacuum cleaner bags, you have plates that are electrostatically charged, and then the dust particles cling to the plates that are charged. The plates are regularly wrapped, the dust falls down and is collected and taken away. The two main technologies for gas cleaning. Okay, and then we move to the turbine. So this cross-sectional picture shows a typical large utility steam turbine. There is a high-pressure cylinder here with control valves. The steam is then expanded through the high-pressure cylinder. This is all on one shaft, taken away to the boiler, reheated, brought back to this intermediate pressure cylinder, expanded. It comes up and flows in this case, two low-pressure cylinders. You can see the turbines are getting bigger as the steam expands and the pressure is lower because the volume increases. The steam expands through these two turbines and then drops out to the condenser, which hangs below the two LP turbines. All of that shaft is then driving this generator at the end of the machine. So that's a typical large utility steam turbine. This is a picture of an IP, intermediate pressure rotor, that's being lowered into the casing. You can see with a man here to give you a feel for the scale. So the complete machine train, if I go back, this complete machine train of HP rotor, IP rotor, two LPs and generator rotor will weigh several hundred tons. It rotates at 3,000 RPM in a 50 Hertz system and is fitted inside the casing 0.2 of millimetre clearances. So this is some pretty special mechanical engineering to make this thing work. Okay, so that's the quick run through coal-fired power stations. Again, to give you a feel for what these things look like from a picture perspective. We're now going to talk about gas turbine power plants. Okay, so gas turbine or Brayton cycle looks somewhat different to the steam cycle. So here, normally we have on one shaft a compressor with blades on it, like the steam turbine blades we've seen, which draws fresh air in. That air is compressed to relatively high pressures. It is then fed to some type of combustion chamber where fuel is added, the fuel is ignited and produces hot gas. Okay? That hot combustion gas is then expanded through a turbine, also with blades in it, exhausted, and that by expanding through the turbine you produce net positive work. So that turbine is also driving the compressor. And about 60% of the work of the turbine is used to drive the compressor. The remaining 40% comes out of the shaft connection here and is used to drive, in our case, a generator. They can also drive things like compressors or other mechanical loads, but we're going to talk about power generation. Okay, so a gas turbine is also known as a combustion turbine because it's combustion gas that drives this turbine. So this is a picture of a large utility. This is, I think, is about a 500 megawatt gas turbine. You can see here the inlet. There's a 17-stage compressor here, okay, with about 24 burners in an annulus around the turbine. Those burners burn into this combustion chamber. It's a circular combustion chamber. And then the gas is expanded through 4 rows of gas turbine blades and then out of the exhaust. So this is a very, very large jet engine. It's the same concept as a jet engine on an aircraft. this one weighs quite a lot more than any gas turbine. So probably the biggest aero gas engines are about 60 megawatts. This is a 500 megawatt gas turbine. So the engines on an A380 are about 60 megawatts if they drive electrical generation. Okay. All right. So this picture shows a gas turbine with the rotor being lowered into position. And you can see there is stationary blading that guides the gas flow and rotating blading on the rotors. And you have to fit this rotor between the blading when you're inserting it. That's a 165 megawatt gas turbine. Okay, so just like coal plants, if you want to build a gas turbine power plant, there are two types: open cycle, which is just the gas turbine with the exhaust gas exhausting to atmosphere, or combined cycle. We'll talk about what they are in a second. And just like the coal plants, a number of site selection issues. So you need fuel supply, normally natural gas, but gas turbines can also burn, for example, diesel or jet fuel. It's called a gas turbine not because it burns gas, but because once the fuel is burnt, you produce a hot gas. Okay. You need a transmission connection, same as coal plants. You need cooling water if you've got a combined cycle plant. You need the geology thing, but it's not as critical as for coal plants. And you need your environmental approvals to build a gas-fired power station. Okay, the two types of gas-fired power station. First one is open cycle. So here the exhaust gas from the gas turbine is simply exhausted to atmosphere, typically at around 400 or 500 degrees C. So you're actually losing quite a lot of heat to atmosphere in an open cycle gas turbine plant. In a combined cycle plant, you exhaust the gas from the gas turbine into a boiler, typically known as a HRSG, a heat recovery steam generator. And that boiler produces steam, which is then expanded through a steam turbine. And you'll get a much higher efficiency out of that combined cycle unit. Okay. There's a slide here for your notes, which is I call it a basic theory slide. So in this particular gas turbine, we're drawing air in. This is a 43 megawatt machine. We're drawing air into the compressor. It's compressed, heated up slightly. Natural gas is brought in the combustion chamber. You produce then hot exhaust gas, expands through a three-stage turbine and out to atmosphere. In this case, we're driving a generator through a gearbox. So in some cases, for smaller gas turbines, you can get better efficiency if this machine is spinning at higher speeds than that set by the generator. So then you have a gearbox in between the turbine and the generator. Okay. One point to note, a very important point to note in operational gas turbines is that the output of a gas turbine goes down as ambient air temperature increases. So typically in the electricity industry, we run gas turbines for short periods in very hot weather because that's when the highest demand is. That's when people run air conditioners. And the irony is, or the problem for the industry is, exactly when you want gas turbines to generate power is when their output is lowest because the ambient air is hot. So you can see here on this machine, this is I think a 16 megawatt nominal machine. So at 15 degrees ambient, it will produce 16 megawatts. At 50 degrees ambient, it only produces 12, and at minus 20, it can produce 21 megawatts. Okay. And the reason is as the ambient air temperature drops, the air inlet density increases, and that improves the output and efficiency of the gas turbine. That's quite an important point in both designing and operating gas turbines. Okay, some really simple pictures now to demonstrate the efficiency issues. So for an open cycle gas turbine, okay, if you've got 100% of the energy in the fuel going in, only about 36% on a typical open cycle machine will be produced as electricity. The rest goes out as losses up the stack. Okay. And an open cycle gas turbine power plant typically looks like this. Is a 2-unit plant. You can see here, the gas turbine is here. This blue thing is the air inlet with a filter housing. So the air is drawn into this filter housing, into the compressor, is burned with the fuel. The exhaust then comes up the stack. This stack gas is of the order of 500 degrees C and goes straight up into atmosphere. Then the electrical connection here to the transformer, and connection out to the grid. So that's what a typical 2-unit open cycle gas turbine power plant looks like. Okay. Combined cycle is more complex, so I have a gas turbine. The air is drawn in, burnt with fuel, exhausted, but in this case exhausted through a boiler, a HRSG, where we're turning water into steam. We expand the steam through a steam turbine. Okay, again, I've got a condenser and I've got losses into the condenser, but I'm producing for 100% fuel, say 17% comes out of the steam turbine generator and 36% out of the gas turbine. Now I'm at 53% efficiency. Okay, we'll see a slide in a minute. Typically, a 53% is a small combined cycle unit. Big modern units can get up to 63% or thereabouts. So a much better efficiency than open cycle, but the capital costs of the plant are much higher. So this is a 400 megawatt unit in New Zealand called Otahu. So you can see here, this is the turbine building. These are the air inlets for the gas turbine. The steam turbine and generator are also in this building. This is the gas turbine exhaust. This big grey thing here is the HRSG, so it's the boiler, and then the exhaust gas comes up this stack. It is now much cooler. It'll be, say, 150 degrees because all of the heat has been extracted by the HRSG, and that heat has been used to warm the steam, which then drives the steam turbine. Okay, and then here a cross-sectional diagrammatic of pretty much the same plant. So here's the HRSG. You can see inside what that looks like. The gas turbine is here exhausting into the HRSG. There's a generator in between the two machines, and then the steam turbine is located here. It's driving the other end of the generator and exhausting into a condenser at the end of the steam turbine. So this is quite a compact 400 megawatts size unit. And then the other option is cogeneration. Not so common in Australia, quite common in Europe and North America, where you have a gas turbine which produces electricity, but the exhaust of the gas turbine is used for some type of waste heat recovery. So typically, if you have a factory that needs heat, this sort of system is used quite a lot because the factory can then generate its own electricity, and the waste heat from the gas turbine, much lower grade waste heat, is then used in the factory process. So the company I work for, we've got a plant like this in Tasmania that makes, of all things, potato chips. So they have a 10 megawatt gas turbine that produces electricity for the potato chip factory, but they use the heat in the process for making potato chips. Okay. In Europe, this is used quite often where they use the waste heat for district heating. So they'll have a gas turbine power plant in the middle of a city, burning natural gas, and the waste heat is used to heat buildings in a number of city blocks. And it becomes a very efficient, so you can get up to 90% heat utilisation by doing this sort of thing. Very efficient way of using heat. Okay, last couple of comments about gas turbines. Modern gas turbines are very highly sophisticated pieces of mechanical engineering. The blading that we saw very quickly in some of those pictures on a high efficiency turbine is very complex, so you can see the geometry, the aerodynamic geometry is quite complex in order to achieve the very high efficiencies. In addition, the highest efficiency you get is a function of the higher combustion temperatures, okay? And what a modern gas turbine has is this very complex series of cooling holes, and there's cooling air blown through the blades so as to form a very thin layer of cooling air over the blades. The combustion temperatures in a modern gas turbine will be above the melting point of the metal in the blades. Okay? And it's only because the blades are cooled by this cooling air, and often they have some sort of ceramic coating as well, that they don't melt. So this is really high-tech stuff. Okay? The other thing that's interesting for me is, you can see here's a cross-section showing internally what these cooling holes look like. In some technologies, these blades are formed in these complex geometric shapes, and it's one crystal of metal. Okay, so for those of you that study metallurgy at some point, that's pretty tricky stuff. Very high tech. Okay, so this picture then just shows a progression over the last couple of decades of the advancements mainly in gas turbine technology as we go from 1991, when the leading combined cycle units were about 50% efficient, through to now, where the leading combined cycle units are about 63% efficient. People have a vision we might get to 65 at some point. Yeah. But it is a law of diminishing returns now. Okay, now I've got just a very short video just to show you a, this is a 14 megawatt gas turbine.
The SGT-400 twin-shaft gas turbine was introduced.
We'll cut out the party political. But you can see here, so this is a 14 megawatt gas turbine. The air is being drawn into the compressor here. There are, I think, 6 or 8 combustors burning natural gas, and then the gas is expanded through the turbine and exhausted up here. So this video takes us through. You can see how this thing works. Cold air is coming down here, being compressed, then channeled back around into these burners, burnt with natural gas. The gas expands through this annulus thing, in through the 4 rows of turbine blades, and then out and up into the exhaust. So I quite like this. This is quite a simple gas turbine. Every gas turbine works something like this. Okay. Okay. So now we're going to talk about generators. So on whether it's a coal-fired power station or a gas-fired power station, they all have an electrical generator connected on the end. Sort of very, very basic electrical engineering. So for a 50 hertz grid in Australia, we have 50 hertz. In the UK and Europe, there's 50 hertz. US, South America, Philippines have 60 hertz. So for a 50 hertz grid, all of the large utility machines spin at 3,000 RPM. They have 2-pole generators. For a 60 hertz grid, they spin at 3,600 RPM. Also 2-pole generators. The way the generator works, this is a cross-section of a generator. I'm just going to flick backwards. That's what the stator looks like. So the stationary circular part looks like this. It has stator windings in it and thousands of laminations of stainless steel, and the windings cut those laminations. This is what a big stator looks like on a crane. That's a 500 megawatt stator. So if we flick back to here, so this is a cross-section. You can see here are the stator windings. They go the length of the stator. The rotor, this part in here, this is what's driven by the turbine. It's spinning in Australia at 3,000 RPM. It has windings in it, so it is a rotating electromagnet with 2 poles. As it spins, those lines of electromagnetic force cut the stator windings and induce a flow of current. Okay, for those of you that did physics, Lenz's law, induce a flow of current that goes up and out of these connections and out to the grid. Okay, and this thing is spinning at 3,000 RPM on a large coal unit. This generator will be filled with hydrogen. The hydrogen cools the generator, and the windings will be at something like 20,000 volts. So it's also quite interesting technology. It's sealed with oil, so the hydrogen stays in, so it doesn't get out to atmosphere and burn, hopefully. And everything in here is at 20,000 volts. Okay. Stator with the rotor withdrawn, in this case, is an old one being withdrawn. Okay. Electrical systems. We're going to talk about this. So this is a single line electrical diagram. All power plants have significant power consumption. So a coal-fired power station will consume about 7% of its own generation, and coal-fired power plants are amongst the biggest users of electricity in the grid. They have their own electrical systems. So if you have a generator here on this single line diagram, a generator circuit breaker, the transformer out to the grid, and then its own supply transformer onto some switchboards that then supply motors and other transformers for other switchboards that drive all of the motors, and there are hundreds of motors on one coal-fired unit. Okay? And the motors will be at different voltage levels. So big motors will be supplied at 11 kV and 6.6 kV. Smaller motors at 415 volts in Australia. So motors up to about this size will be 415 volts. Once you get much bigger than that, then you go up to higher voltage levels so the conductor size can shrink, okay, for higher power. And the largest motors in a power plant will be of the order of between 12 and 14 megawatts in a big coal-fired power station, that sort of size. So they're quite big motors. Yeah. Also in a power station, you will have a central control room in a modern power station, and the whole plant will be able to be controlled by screen-based controls by operators that sit in the control room. They don't need to go out unless something is broken, leaking, whatever else. Okay. And in order to do that, first thing is you have to measure all of the process variables out in the plant. You need to measure pressure, temperature, flow, position, and so on. So there will be, on a typical coal-fired power plant, between 4,000 and 6,000 measurement devices, things this size, that are measuring temperature, pressure, flow, conductivity, and so on. Okay? And then you need to control the flow of oil, fuel, water, hydrogen, whatever it is. So you have devices called control elements that are valves, dampers, circuit breakers that will control all of those things. And that allows you to start and run your power plant remotely from your control room. Okay, and a typical control system in today's world will be fully automated. So you've got screens and some sort of a control room, control computers, PLCs, a distributed control system, and then the so-called I/O devices, all those sensing elements out in the field. Large power plant will also have a significant number of water systems. So some very important people in coal and gas-fired power plants are the chemists who manage all of the water systems. There will be a cooling water system for the turbine condensers, a demineralized water system to produce water that goes around that steam cycle, and that water has to be very, very pure. A condensate polishing system that cleans up that water if it gets dirty for some reason, and a wastewater treatment system to treat any of the wastewater, particularly from the cooling water system. Okay, all these things very important and quite complex to manage in a power station. Okay, grid frequency control. So what I'd just like to talk about for a minute, think about Melbourne with power plants out in the Latrobe Valley. Okay, those power plants are running. We all get up in the morning and we turn on lights and toasters and whatever else. So what happens is, remember right at the start of the lecture, we talked about the power industry being quite different to nearly every other industry in that we have to produce, at any point in time, exactly the right amount of power that everyone's consuming. There's no storage, okay? So if you and I get up in the morning and turn our toasters on and we're consuming more power, how does the power station in the Latrobe Valley know they've got to produce that increment more energy to keep the grid in balance? Okay. The answer is system frequency. Okay. So this whole system, as we said, is spinning at 3,000 RPM, which equals 50 hertz on our AC power that comes out of the power socket. As we turn on lights and toasters and everything else, that additional electrical load looks like a brake on the system. We're trying to slow the machine down. So you've got these 30 or 40 power station units around the country all generating into the grid, and by turning our toaster on, we're trying to slow the system down. The frequency starts to drop. All of those power stations see the frequency drop. They have control systems that are monitoring the frequency, and they recognize they have to put more megawatts in the system in order to bring the frequency back to 50 hertz. So they then start to generate more megawatts. They burn more coal, more gas to generate more megawatts, and the frequency comes back up again. Conversely, when we turn lights and toasters off, the system frequency starts to increase because we've reduced the braking force on the system, and they all back off the coal and the gas firing in order to bring the megawatts back to where they need to be. Does that make sense? That's a very important basic concept in power generation that people don't understand. I think it's quite simple to understand when someone explains it to you. Okay. So very quickly, operations and maintenance. Large utility plants are staffed by operations personnel 24/7. Maintenance people will often work shift work, in some power stations only day work. Nowadays, quite small staffing on sites. And typical power plants, coal and gas, will have some sort of outage cycle of doing outages, major maintenance outages every 3 or 4 years. And at a big power station, a major maintenance outage can cost $50 million. Takes 6 weeks. So the unit, we saw all those pictures of units before, the one unit will be out of service for 5 or 6 weeks. There will be $50 or $60 million spent on pulling many things apart, cleaning, fixing, repairing, putting it back together again, and then running it in for another 3 or 4 years. Okay. Okay, so we're actually pretty close to on time. What I would like to show you now is another short video. So this video is of a maintenance outage on a 165 megawatt gas turbine. Just bear with me. And hopefully that's not too loud. So this is a plant in Queensland, and this outage took about 5 weeks, I think, from memory. So you can see here we're starting to disassemble the gas turbine. This one has 2 very large burner silos either side, so it's a little bit different to the designs we saw earlier. And we actually remove the burner silos. And on a gas turbine, maintenance normally means replacing all of the blades in the turbine, not the compressor, but the turbine where the hot gas is. So in this case, we've got to lift the turbine components out of the turbine house. You can see here the 55-ton rotor is lifted out. Turn it down a bit. Okay, and then the rotor is destacked so as to allow us to deblade the turbine. So it all comes apart. Then various components like these mixing chambers have to be heat treated in order to normalise the metallurgy, so it's good for another 10 years of operation. We do that on site. We recoat the compressor blades, so they do deteriorate somewhat even though they're in fresh air. So this thing is like a 300-ton Swiss watch. It comes apart into thousands of components. They all need to be tracked. Here we're replacing the blades and then restacking the rotor. So there's the rotor completely rebuilt, going back into the gas turbine. Okay, combustion chambers go back. And it's all back together again. Okay, so that's a video that my business did that's actually put together by the customer that we did the outage for, so that's not a party political. Okay. So, again, just to recap, what did we cover? We talked about power industry background, about megawatts, megawatt hours, where are the coal plants, where are the gas turbine plants, what are the issues around the Australian industry, around the transmission network and so on. We talked about coal-fired power plants, how they go together, what the turbines look like, what the boilers look like, the gas cleaning and so on. We talked about gas turbine power plants, open cycle, combined cycle. We looked quickly at what does a generator look like, electrical and control systems, and we talked about grid frequency control. And we're spot on time. Okay, so I'm finished. I don't know if there's any questions about both the lecture or anything else you'd like to discuss about the electricity industry. Happy to have a chat either in front of the group or afterwards, whatever you like. Thank you. Yeah, sorry, man. Yeah. Yep. No. So clean coal is a really misused term.